Yes, we can. That's a triggy one, isn't it? You guys love the trig. Let's see. That's the one, right? 2 cos theta plus sine squared theta?
Yes.
Okay. All right. So we'll start by doing the derivative. So I get that. And I know the critical number, like, first of all, I know the domain of f is all real numbers. And the domain of f prime is also going to be all real numbers because it's all just like sines and cosines, right? So the only critical numbers are going to be from where it's equal to 0. So I'm going to start by factoring out a 2 sine theta. And then we'll apply the 0 product property. So divide both sides by 2. And sine inverse of 0 is going to be pi over 2 plus pi k, where k is an integer. Woo, that's a lot of them. And then we'll subtract 1 and divide by -1. And cosine, so theta is cosine inverse of 1. And that's going to be 0 plus 2 pi k, k an integer. And that ought to do it. So infinitely many critical points here, but that should make sense, right? If this is a trig function, we're going to have infinitely many maxes and mins. And if you were interested, we can always like quick plot f and look at, you know, the maxes and mins going on that, right? So y equals 2 cosine x plus sine squared x. Make that trig style. So it looks like I'm getting a minimum at, you know, pi, 0, right? Did we goof something else up though? So we had this too, and I'm not seeing those. Sine inverse of 0 is here. What did I goof? Did we goof? That doesn't seem right. What mistake did I make here? Rather than hunt for it, I'm just going to cheat and look it up. Oh. Sine of 0 is not at a half, right? Sine of 0 happens at 0 and pi and 2 pi, right? So it's really just this one, because that overlaps all the solutions over here. That makes more sense. Okay. Yeah, you're welcome. Giselle.
Remember 17 for 4.2?
4.2, 17. Okie dokie. All right. So we want to show that this has exactly one real root. This is similar to the example that we did before, right? We did one like this in the notes where we used Rolle's theorem, I think, right, to get the contradiction. So first thing I'm going to note is that if I call this stuff f of x, I can say f of x is continuous for all real numbers. So my first goal is to show that I have one root somewhere, and I'm going to use the intermediate value theorem to get that. Now, easy way to do that is just pick like f of -1. So -2 plus cosine of -1. Well, that has to be negative, right? Because the biggest value at worst cosine could be +1, which will still give me something negative. And I'll do the same thing with +1. So I get 2 plus cosine of +1, which again must be positive because the smallest cosine can be is -1. So by the intermediate value theorem, since f of -1 is less than 0 is less than f of +1, there exists some c on the interval from -1 to 1 such that f of c is equal to 0. So we got at least one real root in there. So assume, for the sake of contradiction, that there exists some c, what do we do? We did c star or something. On that, in the domain somewhere, such that c star is not c, and f of c star is equal to 0. And then let's just say, that c star is smaller than c, right? Like it doesn't really matter, but like without loss of generality, we can just assume one of them is bigger than the other, just to make, for clarity's sake. Cool, so far so good? All right. Since f is continuous and f of c equals f of c star, which is all equal to 0, and f prime is differentiable, and I know that because f is the sum of a polynomial and a trig, right? So if I take the derivative of that, and maybe I should be more specific than trig, of cosine. So I know that that derivative is going to exist everywhere. So I have the three conditions necessary for Rolle's theorem. Good. Okay. So by Rolle's theorem, there exists some k between c star and c such that f prime of k is equal to 0. So let's check out what f prime is. What was that? It was 2x plus cosine, so it's going to be 1 minus sine x. That's 0. No, sorry. It's 2 minus sine x. There we go, right? And if I solve that, I get sine x is equal to 2, or x is equal to sine inverse of 2 which we know has no solution because 2 is outside of the domain of sine inverse. And that's my contradiction. Because now Rolle's theorem fails. Does that feel okay?
Mm-hmm. I just didn't know how to like really explain it.
Yeah.
Just like doing the derivative and setting it equal to 0 and that. I just didn't get the paragraph part.
Yeah. So just explaining why you're using, that you can use Rolle's theorem here now. And then, so let's check that condition, the conclusion of Rolle's theorem, that should hold.
Yeah.
Because we've met the criteria beforehand. Oh, but it doesn't hold, it fails. And that's why, okay, so there couldn't have been a second one. Because if there was, this other thing that we know is true doesn't work.
Right.
That's what we're saying. Does that feel okay?
Yes.
And the more times you do something like that, the easier and clearer it becomes in your head. But the first time, it's like, that's a lot to wrap your head around.
Yeah.
Others, homework questions? Yeah, Knowles.
Could you do 31 through
4.2, number 31? Sure hope so. Oh, that's a good one because it's piecewise, huh? All right, it says let f of x equal 1 over x, where we do 1 over x if x is less than 0, and 1 plus 1 over x is if x is, 1 over x if x is greater. Why do they write it that way? That's a dumb way of writing. I would do the first part of the domain first and the second part of the domain second. Why x greater than 0 and then x less than 0? That bothers me. Anyways, fine. Show that f prime minus or is equal to g prime for all x in their domain. Can we conclude from corollary 7 that x minus g is constant? So let's start just by doing f prime. So remember, f prime is just going to be the derivative of x to the negative 1. Or negative 1 over x squared. And this is, again, if x's are not equal to 0, right? How do I do a derivative of a piecewise function? Well, I just differentiate each piece. And what is this just saying? So that part's done. Let's check and read what corollary 7 says again. And see if there's a continuity condition there. If f prime of x is equal to g prime of x for all x in an interval from a to b, then f minus g is constant on a to b. That is f of x equals g of x plus c, where c is a constant. Okay. So I don't think we have that exactly. Because the interval from a to b would include 0, which is not part of either domain. So we could say that like f minus g is constant from like negative infinity to 0, and we could say it's constant from 0 to positive infinity, but I don't think we can say it's constant from negative infinity to positive infinity. Would be my suspicion here. Let's look up what the answer is. Does that, you buy that, Nolan?
Yeah.
I think that's probably where we're going, or what we're driving at on that one. But let's see what the, yeah, so that's exactly what they're saying. So that part's true and that part true, but f minus g is not constant from negative infinity to 0, union 0 to positive infinity, which is the domain of f and g. So you can say like the first half of it, those are constant, you know, or f minus g is a constant. And the other half of it are a constant, but like all together is not. Good?
Yes.
Okay. And the reason is because the domain here is not an interval. It's the union of two intervals where there's a break in there. So last call on questions. All right. 4-3 it is. So 4-3, we're going to continue on our discussion of like, what can we learn about f from looking at the derivative of f, right? So in 4-1, we talked a lot about, kind of culminated with this idea of the absolute max and min test on a closed interval, right? If I have a closed interval and a function, I can find the relative or the absolute mins and maxes by looking at where the derivative is 0. I should say the critical values, not just where the derivative is 0, but the critical values along with the endpoints. And just the biggest of those, that's our maximum, and the smallest of those, that's our minimum. Done. What we want to do today is kind of figure out, okay, what do I do if I want to also worry about local mins and maxes? Because if I just look at a list of values, other than the biggest and the smallest, I couldn't tell which one is a max or a min, right? -2 could be going down like this, or it could be going up like that, right? I don't know just from what we did before if the others are going to be local mins and maxes, or maybe nothing at all, right? They could go like that and be nothing. So we're going to start with a definition. We say that f prime of x greater than 0 means that f is increasing wherever the derivative is positive. Okay, that makes sense, right? If you're positive slope, then the function should be increasing as we go from left to right. And likewise, then f is decreasing where the derivative is less than 0. So like, makes sense to me. So let's do an example here. It says, find where the function f of x is equal to yada, yada, yada is increasing and where it is decreasing. So to do that, I'm just going to start by looking at the derivative. And then I'm going to find where the derivative is 0. What would I want to do to solve this polynomial equal to 0?
Factor out an x, and then
How about a 12x, right?
12x, yeah. And then factor the inside.
And then we could either use the quadratic formula or factor the inside. The inside is factorable. Let's do that because that looks way easier. So that tells me 0, 2, and -1. So now what I'm going to construct is a sign diagram, like we did in pre-calc to solve polynomial inequalities. So I'm just going to pick a test value that lies somewhere inside of each interval. So something less than -1, something between -1 and 0, something between 0 and 2, and then something bigger than 2. And I'm going to plug that into f prime to see if I get a positive or negative value. Now, I'm not actually going to plug anything in and evaluate this. I'm just going to say take -2 and plug it into each piece I just look at whether each piece is going to be positive or negative, right? So when I plug into 12x, I get a negative. I plug into x minus 2, I get a negative. I plug into x plus 1, I get a negative. The product of three negatives is negative. I'll do the same thing with negative 1/2 when I plug into 12x, negative. Plug into x minus 2, negative. Plug into x plus 1, positive. Two negatives and a positive is positive. I plug in 1 to 12x, that's positive. I plug in 1 into x minus 2, that's negative. I plug 1 into x plus 1, that's positive. Positive times positive is negative. And I plug 3 in, that's positive in all three places. So my intervals where we are increasing are going to be these. And the intervals where we're decreasing would be the other, well, let's not circle them because that doesn't tell us anything, are the ones that are remaining. Does that feel okay? This method should look familiar, right? We've used this technique of building a sign diagram before when we solved polynomial inequalities last year in pre-calc. I remember doing it.
You're teaching it now.
Yeah. Does that feel okay? Pretty straightforward, right? How does this differ from what we did last year? Because you just take the derivative first and then you do the same thing that we did last year, right? This leads us to our second derivative test. This is one test we can use to determine whether those critical values, -1, 0, and 2, are maxes or mins. So if I look, it says, suppose C is a critical number of the continuous function f. If f prime changes from positive to negative at C, then f has a local maximum at C. So if I look, that happens at 0, right? 0 changes from positive to negative. You guys see that? So that's a maximum. And then if f prime changes from negative to positive at C, then f is a local minimum. So -1 and +2 are minimums. Everybody cool with that? So how much work is this additional to the sign diagram? Virtually nothing, right? I just look at the result of my sign diagram. Now, one piece of caution here, this only is going to work if you have all the critical values. If you miss one, like you forgot to look for where the derivative was undefined, you're going to mess this up. Okay, just as a word of warning. So what we did here was reliant on us having found all the critical values. Because if you're doing test values in between and you don't know that you have all the critical values, you can't make this conclusion that, oh, I know the graph with one test value, I can tell everywhere on that interval is going to be positive or negative. Can't do that unless you know you have all the critical values. Cool? And then part C says, if f prime does not change sign, goes from positive to positive or negative to negative, then that's not a min or a max. What it is like something that did that. For example, that's positive to positive. Everybody's okay? Because you can see here's where the derivative would have been 0. All right. And here's our graphical examples, right? So this is from increasing to decreasing, that's a maximum. Decreasing to increasing, that's a minimum. Increasing to increasing, that's nothing at all. Decreasing to decreasing, that's nothing at all. Everybody cool? Pretty nice, right? That's a pretty effective, simple test. It scaffolds on nicely to a skill we already feel pretty good about. We already did this example here because I went in and wrote min and max next to the stuff after we did it. anticipating that we would do this. Let's do another here. So it says, find the local max and min for g of x equals x plus 2 sine x, where x is between 0 and 2 pi. Notice this is a closed interval, right? So I could still use the closed interval test on this to find the absolute maxes and mins, but I want only the locals. Now, if my absolute max or min happens at an endpoint, does that count as a local? No. So I don't need to check the endpoints here. All I need are the critical values, even though it's on a closed interval. If this was asking for absolute maxes and mins, then yes, I have to check the endpoints as well. Everybody's good? So if it asks me, for example, both the absolute maxes and mins and the local mins and maxes, I'd have to do the closed interval check for the absolute mins and maxes, and then also do the sign diagram to get the local mins and maxes. Okay? All right, so let's do this. Start by taking the derivative. I'll note that g of x is defined for all numbers on that interval, right? Since it's a polynomial plus a sign. I'll notice that g of x is defined for all x on that interval since it's a polynomial plus a cosine. Set that equal to 0 because those will be my only critical values. So I subtract 1 and divide by 2. So that should be cosine inverse of negative 1/2. How many times from 0 to 2 pi will cosine inverse equal negative 1/2? Twice. They should be at 2 pi over 3 and 4 pi over, or no,
6.
yeah, no, sorry, 7 pi over 6, and then, nope. I want 1/6 more than a half. What is that? No, that's 2 pi over 3, right? A half plus a sixth is 2/3.
No. No. Wait. Yes.
Okay. And then also 1/6 less than 1.5. Right? Should be like here and here. Agreed? So that's like so what? 9/6 minus 1/6, so 8/6, or 4 pi over 3. Okay, that's what I thought it was going to be. I'm doubting myself. So those are those. Build my sign diagram. So I'll do like pi over 2. I'm sorry, let's put these in the right place. 2 pi over 3, 4 pi over 3. So something less than 2 pi over 3, well, a half is less than 2/3. Something between 2 pi over 3 and 4 pi over 3, well, that can just be pi. And 1 and 1/3, well, 1.5 is more than that. So those will be my test values. If I do that, cosine of a half is 0. So that's going to be 1 plus 0. Cosine of pi is negative 1. So that'll be 1 minus 2. That'll be negative. And then 3 pi over 2 cosine is 0 again. So that'll be positive. So we go from increasing to decreasing. This is our max. And decreasing to increasing. That'll be a min. Now, be careful here because it asks for max and minimum values. So our maximum value is going to be g of 2 pi over 3. And our minimum value is going to be g of 4 pi over 3. So you'd want to plug those back through g. I'm not going to do that right now because it's just plugging in at that point, right? Does that feel okay? Just be cautious when you're asking for the maximum or minimum value. They'll want the y coordinate, right? So it's not looking for 2 pi over 3 and 4 pi over 3. You need to plug those back into the original. Needless to say, on an AP exam, in the multiple choice, they would have the x coordinate as one of the choices to make sure that when you read value, you know that you should be giving a y coordinate, not the x, which is really lousy, right? It's like you're going to trick me a bunch of times on that, and I'm just for me not reading closely enough because I'm in a hurry, and sometimes it's hard to read super close. So now we're going to look at what the second derivative can tell us about f. So before we do that, we're going to start with the definition. So we're going to talk about concave up and concave down. So we say if all the tangents for a graph or on some interval are below the graph, then that means the graph is concave up. So that's what you're seeing here. The blue line is our graph, and the pinks are examples of tangents. Notice that the blue line is above the pink line for all. So we'd say that that is concave up. I usually think about it as like, can it catch water if I dumped water in there? And then we say if the opposite is true, if the graph is below all of its tangents, we say that's concave down. And I think about it as the opposite. If I pour water on that, it just all runs off, right? Cup versus dome. Okay. So if I look at this graph here, we can see on the interval from A to B, that is concave down, right? Because if I pour it on, at B, we switch to concave up because it's catching water. At C, we switch, it becomes concave down because we're dropping water. At D, we switch again, becomes concave up. At E, still concave up. Here at P, we switch to concave down. Can you guys see that visually? All I did was look with my eyes. So again, I looked at if I dumped water, would it run off? Yes. If I dump water, will it catch? Yes. So that's all I'm doing. Just looking with my eyes. Now these points where we change concavity, we'd call these guys inflection points, where the concavity of the graph changes from concave up to concave down or concave down to concave up. We call those guys inflection points. Let's look at how we can check for concavity and inflection points using calculus. So if the second derivative is positive, that means the graph, or f, is concave up at that spot. If the second derivative is negative, then the graph is concave down on that spot. Everybody okay with that idea? Positive, concave up, negative, concave down. That should be pretty easy to remember, right? Positive and up seem like they go together. Negative and down seem like they go together. All right, I'm skipping that example. And we said a point P is called an inflection point if f is continuous there and the curve changes from concave up to concave down or concave down to concave up. Right? So it wouldn't count. something like that doesn't count as an inflection point if we don't have continuity, even though there's a change in concavity there. You guys kind of see that? That's the thing you have to be careful about. All right. So let's look at this example here. It's given us some criteria and asks us to sketch a graph. Come on now. There you go. All right. So let's see. Looking at the numbers, it looks like I care about 1. I'm going to care about -2. I'm going to care about +2. And then I'm going to care about y = 0 and y = -2. So I can see that this is like an end behavior, right? We've talked about that before. We're going to have another end behavior here. So what I'm going to do is I'm going to do some highlighting to remind myself what's going on for each of these intervals. The first derivative greater than 0, that tells us we're increasing. So I'm going to highlight that. And the second derivative, or the first derivative less than 0, that tells us we're decreasing. So I'm going to do that. The second derivative positive, that means we're concave up. And that happens in 2 spots. And then the second derivative being negative tells us that's concave down. That's happening in that spot. And now I'm going to start trying to draw my graph. So I know we're following -2. Oh, let's also point out that we're changing from increasing to decreasing at 1. So that's going to be a maximum, right? All right. So I should be following -2, and we should be increasing and concave up. And we should be switching to concave down right there. That looks like what's happening. Oops. And then we're switching then to concave up, because we start decreasing once we get to 1. So this is like my inflection point. This is like my maximum. That's my other inflection point. And this is my end behavior. And this is my other end behavior. Does that feel okay? That's going to be hard initially. If that feels hard, it's going to be hard initially. Just go slow, do some highlighting, put in the points as you kind of go. If you know something's going to be a maximum, kind of like, or something's going to be an inflection point, that helps you when you're drawing to know, like, okay, I just got to like connect things to here. You know what I'm saying? And usually if you can get everything connected up, like the concavity will end up working out for you. It's usually not the first thing I'm trying to worry about. Additionally, in addition to concavity, the second derivative can also, in conjunction with the first derivative, tell us if something is a local min or a max. So, assuming that the second derivative is continuous near C, it doesn't need to be continuous everywhere. But if it's continuous near C, if the first derivative is 0 and the second derivative is positive, that means we have a minimum. And if the first derivative is 0 and the second derivative is negative, that means we have a maximum. Now that's reverse of what your intuition would hope to say, right? Like positive means minimum and negative means maximum. But we can deal with that. All right. So it says here, discuss the curve y equals x to the fourth minus 4x cubed with respect to concavity, points of inflection, local min and max. I'm not going to sketch afterwards. So if I want to do extrema, I'm going to start by taking the derivative. If I take that derivative and set it equal to 0, I can factor off a 4x squared. So I have 0 and 3 as my critical values. Obviously, there's no place where this function is undefined because it's a polynomial. So if I do my sign diagram, if I plug a -1 in, I get positive times negative. If I plug a 1 in, I get positive times negative. So 0 is nothing. If I plug a 4 in, I get positive times positive. So we change from minimum, or from decreasing to increasing. So x equals 3 is a local minimum. Everybody feel okay with that? Actually, maybe we'll do... Write it down here. And then let's do the second derivative. So that's going to be 12x squared minus 24x. If I set that equal to 0, I can start by factoring out a 12x. So x equals 0 and x equals 2 are my possible inflection points. I'm going to do the same thing and do some test values. If I plug -1 in, I get negative times negative, that's a positive. If I plug 1 in, that's positive times negative, that's negative. If I plug 3 in, that's positive times positive, so that's positive. So I see that x equals 0 and x equals 2 are both inflection points. And I notice that we are concave up from -infinity to 0 and 2 to positive infinity. And we're concave down from 0 to 2. I think that answered the first part, right? Discuss the concavity, the inflection points, and the local mins and maxes. Now, alternatively, I could have also taken those two inflection points and done like the second derivative at 0, which I can tell is 0. So that tells me it's not a min or a max because it's not positive or negative. And do the second derivative at 3, which I can tell is going to be positive, which tells me that's x equals 3 is a minimum using the second derivative test. So I could have done that instead of drawing a sign diagram. Did 6 in one, half dozen in the other. There will be situations where only one of them, like I can cook up a problem so that like only one of them is possible to do. Casey's looking at me like, oh, what's that would look like? You'll see when you do the multiple choice. But those are your two techniques for finding local mins and local maxes. The rest of these examples are more of the same. So I'm probably going to stop here. I want to point out to you guys that this morning I put in the key for the multiple choice questions. So I have like worked out solutions on like how I did some stuff. A couple of these I crossed out because I realized with the question that I chose, it involved some stuff that we haven't talked about yet. So a couple of these I just crossed out on the key where it's like, oops. Because I was reading through, I was like, yeah, we can do that. And realizing, oh, no, we can't. I'm working on the free responses right now. I hope to have those up and posted before we go on break. Alrighty.
Bye, Mr. Kulik.
That was really good timing by me, though, like right at the bell.
Mr. Kulik, so is it okay if I work on the questions during break?
Yeah,
Okay.
yeah, please. When we get back, we just have L'Hopital rule and a review day.
I mean, for me, it's not like...
Well, yes, you have, and you're going to be gone even when we get back. Thank you. You're welcome.
You guys and Joey, Mr. Kulik won't be here.
Okay.
That week.
And Nolan. Oh,
I'm
boy.
sorry.
Okay, like this whole class. Got it.
Mr. Bullock?
Yes.
So we have bio and math finals on the same day.
Oh, no.
And I can do it, but I know that clearly I got burnt out. And I'm just not trying to take that chance for that to happen again.
I understand.
So like,
Do you have
I have a study hall.
a study hall?
I have an 8th hour.
I am more than happy to let you guys, take one or, like,
Yeah.
whatever's easiest and take on, in the 8th hour. If you want to do bio or you want to do bio. I am perfectly amenable to teaching.
Yeah. It's just like
if your bio teacher's like, then come talk to
Probably.
me. Then come talk to me because that's fine.
Okay. I just
Yeah.
saw what happened last test. I was like, I'm not trying to have that.
Yeah, I didn't take
final.
bio that day. I had
Yeah.
so.
Yeah.
I
So
shouldn't have.
I don't want that to happen either.
Yeah,
Right.
me either.
So remind me when it gets close, and I'll make sure that everything's in the right place. But that's
Perfect. All right. Thank you so much. Have a
of
good
course you too.
Borrow this one. You can tell the joke or what?
Oh,
Let's hear it.
what's the best time to go to the dentist?
2:30.
You knew that.
Sure. Your 6th hour, right? Yeah, no problem.
It was getting a little.
Yeah, I can see that it's been seen some better days.
Come on! It's a ball! Come on!
I have the note card.
Perfect. Thanks, Ellie.
No problem.
Isaac, how many beans did you put in your bean soup? 239. Because if you added one more, it'd be 240.
That's pretty good.
Slap that knee on that one.
I'm so hungry. What? It feels like so, yeah.
It's so weird. Yeah, this is actually like on bad. This is like, dude, we should have a candidate. Yeah, why the first hour, bro? Why that's easy. Yeah, who knows? Did you not
Can you not go through my backpack, you weirdo? If I go in your backpack, I'm gonna find something you don't want me to find.
What is it? Whoa, what is that supposed to mean?
Yo, Jack,
I think I got you.
No.